speaker of this year is Seunghun Lee, Binghamton University. He did PhD at Heise on the Holmsen.
Thank you for introduction. And the title of this talk is the Transversals and Colorings of Simplicial Spheres. And unfortunately or fortunately, this is not a really kind of a rigorous talk. I mean, this does not really provide any rigorous mathematics at all. But it is more like a personal recollection about around just one problem. And there were many people, not only these three people, but there are many people involved in this. And also this one additional person. But for for the result, which are concerned in this presentation, I mean that these four people, including me, are main characters. So one person is Joseph Briggs at Auburn University. Now he is assistant professor in the Michael G. Dobbins, and I'm also a postdoc at Binghamton University. And so there is another person, Chris Ippolito, who is a graduate student at Binghamton University. And he's already a kind of the very great expert in, I think, category theory and the algebraic side of combinatorics, and from whom I get many help from. Okay, so I'll start with the pictures. And this is the Joseph Briggs and the Michael Dobbins and Chris Ippolito. Yeah. Okay, so I'll start from the first piece. So this presentation has the three pieces of my personal recollections, and in the first piece, I like to introduce the polytope transversal problem first, and that introduction will be also relevant with the second piece and third piece. Okay. Yes, so the first piece will be a little bit longer, So even if these three pieces are related to one problem, so those results might look like quite independent results. But to me, they are quite interconnected, quite closely related to each other. Okay, so I'll start from the first piece. Okay, so around 2015, I was a master's student under Professor Holmsen. And at the time, Professor Holmsen asked me the following question. So this is a more general question, and I like to specify the statement a little bit more. And this is the general question. What is the transversal number of a d plus one-dimensional simplicial polytope? So for this problem, we first need to ask what do we mean by asking the transversal number of a polytope? Because a polytope, basically, polytope is defined as a geometric set. I mean, it is the convex whole of the vertices which are in convex position. So what we mean by asking the transversal number? So we are asking the transversal number of a hypergraph which arises from the polytope. So that is my answer. So for a hypergraph H, which is on the ground vertex V and the collection of edges E. We call T a transversal if for every hyper H E inside the edge set E there is a vertex V in T such that the V pierces the hyper H E. Okay, so this is I think you're familiar with this definition. Also, you're familiar with this definition of the transversal number. We read of this as a transversal number, and we denote it by tau. And tau H, the transversal number of H, is the minimum size of a transversal of H. Okay, and so for a polytope, when we consider the transversal, we consider the so-called facet hypergraph of P, which means that so this is just a collection of the vertex set, vertex subset, where the vertex subset is coming from the facets. I mean, this is just a collection of the vertex set of each of the facets in the of a given polytope P. So maybe you can understand it much better by seeing these simple examples. So if you just see the left picture, you see the tetrahedron, right? On the right-hand side, you see the octahedron. So for the tetrahedron, actually, we collect all the vertices for each of the facets. So how many facets are there? Obviously, there are 4 facets, right? And for each of the facets, we collect the vertices, V1, V2, V3, up to the V2, V3, V4, and so on. And as you can see, these orange vertices, 2 orange vertices become a transversal for this tetrahedron because this vertex covers this facet. Maybe I should come closer. This facet, do you see V1, V3, V2, and V1, V3, V4, and V3, V4, V2, right? And for the remaining facet, this V1, V2, V4, V1 covers the remaining facet, right? So this becomes the transversal. On the other hand, for an octahedron, as you can see, so there are 8 facets here, and so we can choose the 2 antipodal vertices here as a transversal, W1 plus and W1 minus. Okay, so this is how we get a transversal from a polytope. Okay, so there is one thing that I want to say about it. Actually, so when we say something about a polytope, so polytope is as I said, it is a convex hull. I mean, it should be a convex set. But here, actually, if we go into the facet hypergraph, we only need the information about the boundary, right? So here we only care about the boundary information, not the interior. Okay, this is the all things that we care about. Okay, and so by using these definitions and convention, I like to present a more precise version that Professor Holmsen presented about the 6 years or maybe 6 years ago. And this is a more precise version. Is there a alpha d which depends on the dimension d, which is strictly less than 1, such that for every d plus 1 dimensional simplicial polytope P, we have tau P is at most alpha d times n, where n is the number of vertices. This was the question. Okay. So this looks a very nice and interesting question, but actually, if you see the following conjecture, this looks very surprising. Actually, this was his conjecture. He conjectured that alpha d is exactly 1/2 n plus some small o of n for every simplicial d plus 1 polytope. And this conjecture is still alive. So if you are interested in this problem, then you can consult with Professor Holmsen after this talk. Okay, so, but actually, so one can ask why we are caring about this conjecture. What on earth we are caring about the transversal number of polytope or any geometric shape? Why should we do that? Actually, there is a motivation from combinatorial geometry. And actually, it is related. It has a connection to the Professor Holmsen's earlier paper with Yanoshi Pach and Tverberg from 2008. And actually, that paper is divided into the 2 big themes. And so I think they are, even if they are related, maybe one can say that they are also independent topics. And one of the first topic that is considered in this paper is the surrounding property, SK. So the definition is the following. So for a point set P, so P is a point set, not a polytope. P is a point set in general position with respect to O, so the origin O. It means that, so the general position concept in here means that whenever you choose D vectors, so D points as a vectors in the Euclidean space or less, they should be linearly independent. Okay, so this is the definition of general position in here. Then, so if you have this kind of point set, P set to satisfy SK, or it is also called the K-surrounding property. Another name of SK is K-surrounding property. And its definition is that if any K subset of P can be extended to a D plus 1 subset, in other words, a D plus, so simplex Q of P such that that simplex captures the origin, right? Okay, so actually, if we think about the P, if we think about the point set P in RD with a size greater than or equal to D plus 1, and if a convex hull of P captures the origin, then so it is just a reformulation of the earlier very famous theorem. And then this instead there exists some Q, so then P satisfies S0. Is there someone who can guess what this theorem is? So actually this is, have you ever heard of Kara-Theodori theorem? So this is actually equivalent to the Kara-Theodori theorem. Kara-Theodori theorem. Okay, so what I like to say is that this surrounding property is seem to be so I think this is a kind of effort to generalize the Kara-Theodori theorem in the two extremes. And in this paper, they have also shown that actually for the SD, for K equals D, for the case when K is equal to D, this surrounding property is not really not satisfied in general. Whenever the size of P is greater than D plus 1. Okay, so yes, it is a kind of effort to search for the another extreme of the Kara-Theodori theorem using the quite new parameter and the new concept. And in another extreme, not only S0, actually there exists an arbitrarily large point set in RD with this surrounding property. So maybe I can draw the one diagram here. So actually at that time I was working on the generalizing this concept, I mean this result to the oriented matrois. That's why I succeeded that Professor Holmsen suggested and drew this diagram to me, which looks very mysterious to me still. And this is something like this. So what is the dimension? Yes, this is a K, and this is the dimension. And so dimension is going higher with this direction, and K is also going higher with this direction. And this line is asymptotically K is equal to D over 2. Okay, so we know that actually this does not only say about this case, but as far as I remember, this covers all this. Okay, so for this region, we know that surrounding property as something, SK, works quite well. But for this extreme, we know that SK does not work well. Okay, so we know about this. So his question was that what about the inside here? Can we increase the K? Can we increase the K, the value of the K, to satisfy the surrounding property or not? That was the question. That was the question, but actually I could not really think about the problem. So I could not really have any progress about that problem. But actually, this is a quite a so how can we obtain this construction? I mean the arbitrarily large point set in RD. Actually, I think this is a quite quite deep result, I think. This is coming from the cyclic polytope, Gale duals of cyclic polytopes. And let us look at that. So what is the Gale dual and what is the dual itself? And why do we consider about that? Actually, there is a concept which is called the Gale dual, which sends an arbitrary point set to another point set in Rnd-1. So if we have a point set P in Rd, and by using the Gale dual operation, this sends another point set P star in Rn-d-1. Actually, this Gale dual is not unique, but if you just think about the dependent information about dependency, linear dependency, or affine dependency, or independence, actually, so this information is uniquely, that information, that combinatorial information is uniquely determined by using the Gale dual. So that is why I use the in here, the dual property, so the in here, the Gale dual P star OP, and the Gale dual P star OP. And this dual property is actually equivalent to the original property, primal property Sk, in the sense that P satisfies Sk if and only if P star satisfies S star K. And so for when P star forms a polytope, so actually this is not really like a special case, but actually this holds a general, but it is very hard to explain. So it is a little bit more complicated for a general case. But when P star forms a polytope, P star satisfies S star K if and only if the convex whole P star, the facet hypergraph of this polytope, has no transversal size K. In other words, the transversal number of that facet hypergraph is greater than K. Yes, so that is the connection. Okay, so let us look at the cyclic polytope case once more. Actually, when we use the notation D star in M, so as a m-4, m-d-1, then the D over 2 plus 1, this was the number of the second results of the previous theorem, right? So this was that number, and if we express that number with the dual dimension D star, it becomes this number, right? Actually, this should give a lower bound for a transversal number, and the easy thought can also gives that actually the transversal number is exactly this one. And as you can see this becomes n over 2. And why this is interesting? Why it should be interesting? Because a cyclic polytope is neighborly, and by the upper bound theorem, by Magnum-Lamb, or by the upper bound theorem Stanley for simplicial spheres, this should attain the maximum number of facets, which means that this does not imply, but we might think that, well, this might need more and more transversal number, right? So than the usual ones, because it has many facets in here. So that is that n over 2. It looks very plausible when I looked at the conjecture first, and I strongly believe that. But maybe one can doubt it, but we will see more and more examples. Okay, so this was the more ambitious version that we have shown this before. Yeah. Okay, so let's look at the more examples. Yes, when d is equal to 1, this is only the case that it does not satisfy exactly, but still asymptotically this is n over 2, ceiling of n over 2. And this one sphere, so combinatorial people maybe will not use the one sphere or the one-dimensional sphere. You will say that it is a cycle, right? And the cycle has a transversal number, ceiling of n over 2. And this is the case. And this was an easy case. But what about the two-dimensional case, two-dimensional sphere? For simplicial two-sphere, we have this one. Actually, this is not the result of them. So their questions and their results were a little bit different. But actually, they used the idea. So they have shown something different using but still very related result with this using the four-color theorem. Can you guess that how to use the four-color theorem to get this theorem? Yes, some people know the answer, but I like to give another chance to other people. The hint is that after we use the four-color theorem to color the graph of the two sphere, I mean the planar triangulation. Planar triangulation, so not planar, but two-dimensional triangulation of sphere with the four colors, I mean the graph. And then we choose some color classes among them. How many color classes should we choose? So what if, yes? Somebody talks. So what if we have just to choose one color class? Then maybe, so let's use all the colors. So let's suppose that we have used white, yellow, blue, and red, right? Suppose that we have chosen just this one color class, which is white. Then there might be a triangle which uses the other color classes, right? So in this case, these white vertices do not pierce this triangle. Do you agree with that? Yes. Okay. So what about choosing two color classes? Do you think that will be the transversal? Yes. Yes. So on the other hand, if we choose two color classes, there should be a transversal, because anyway we need to use at least three colors in here, and there are only four colors. So if we choose two colors, there should be there should be a color which is used in this transversal and also for every triangle, right? So that shows that actually choosing the two color classes is the right answer for this problem. So by using the four color theorem, there is a coloring using the four color classes, and we can just choose the minimum size, two color classes of minimum size. That shows that the transversal number of the simplicial two sphere is bounded by n over 2. Not only that, so there are many examples. So for a stacked D sphere, the transversal number is bounded by 2 over d plus 2 times n. So there is something called stacked D sphere, and this also satisfies the n over 2 bound. So if we start from the d equals 2. And also, so this was the construction by Miyata and Penrose from 2015. And so in that library, we can see the many neighborly oriented matroids of small ranks and the number of vertices n. And so actually, this should not be vertices, but this should be number of elements. Okay, and they all satisfy the n over 2 bound. And the many neighborly spheres by Novik and Zhang in 2021, it is a quite recent result. They all satisfy this result. This all satisfy the n over 2 bound. They even satisfy the more stronger property. But anyway, so I'll proceed. So if you just see the all results like this, and especially the last result about the neighborly spheres. So yes, so if you believe that, if you think that the neighborly spheres should satisfy, so should have the larger transversal number than yes. So this n over 2 bound looks very promising. So I asked this more general question, and so I asked this question to many places and to many people, and usually they believe it. usually they believe the conjecture and they try to figure out how to prove this conjecture. But when I arrived at Binghamton University and in the last year, when I presented this problem in there, the graduate students, Chris Ippolito has said that I bet it is false. And so it was a very interesting response to me. So I asked him why. And he said that because in the 4th dimension, anything can happen. So actually, this does not mean anything. This does not mean anything. But yes, right, yeah. But actually, this is essential 3 dimension, not 4 dimension, because we are So actually, so we have covered the 2-dimensional sphere case. So the next case should be 3 dimension. But the 3-dimensional sphere should live in the 4 dimensions. So this is why he said that. Even if this looks like, so it is not a proof, definitely. But actually, it gives me a feeling that maybe it can be false. So so I start to follow that direction. And actually, yeah, I could find with the joint work with Joseph Briggs and Michael Dobbins, we could find the arbitrarily large Simplicial 3 spheres with transversal ratio at least 11/21. As you can see here, this is a slightly bigger than 1/2. Okay, so yes. Anyway, this general conjecture is false, but still, Holmsen's conjecture is not known. I mean, the answer for Holmsen's conjecture is not known because it is about the polytopes. Okay, so let us see how it is constructed. So, but before going into that, I need to introduce some basic concepts and notions. Huh? So that is a good question. So unfortunately, we don't have any upper bounds for this problem. Yeah, upper bound for the transversal number. So we don't have any non-trivial upper bound for the higher dimensional problem. I mean, the D is at least 3. Okay, and I'll only introduce all the concepts in the 3 dimension. And in 3 dimension, Simplicial 3 sphere is neighborly if this sphere contains the complete graph as a 1 skeleton. And the Simplicial D ball is called the stacked ball if there is a sequence of stacked Simplicial D balls from B1 to B, such that Bj plus 1 is obtained by attaching a D-dimensional simplex to Bj at the boundary for every j. So maybe this is very complicated, so let's look at the 2-dimensional case. Actually, the 2-dimensional case is nothing but the maximal out of planar graphs. We start from the one triangle, we add another triangle at the boundary, and we add another triangle. So this orange triangle is a new triangle, and this orange triangle is always attached with the new triangle, so at the boundary. So the previously constructed complex at the boundary, like this. So you can just think about this stacked ball as a kind of the very similar thing with a stacked outer plane or something. Okay, but we need to also care about the whole faces inside there. Okay, any question about this concept? No. Okay, then how? So let's look at this. So that there is a proposition. There is an inductive way to construct a neighborly sphere, but so this is the way basically. So this proposition is stating the inductive constructions. But let us look at this picture. So this is the previous neighborly sphere. And then what we do is, actually this is a very misleading picture because in 2 dimensions there is this kind of situation should not happen. But let us look at this picture. Then what we find is we find the stacked ball as a subcomplex inside K, such that B is a stacked 2 ball, and also the B covers all the vertices of K. In other words, all vertices are at the boundary of B. Okay? Since the in the outer planar graph, every vertices are at the boundary, right? So we have this. Then we add a new vertex at the top, and we add all the edges like this. Then this gives all the edges between them. But what about the edges between them? So this should be also satisfied because K was supposed to be neighborly sphere, and also in the higher dimension, not only the vertices but edges should be at the boundary. Yes. So this construction gives another neighborly sphere with one size higher. Okay. So this is the inductive construction, and this is a kind of the main ingredient that I wanted to use. So basically what I did was the following. So this is the computer experiment, so the construction by computer experiment. And I started from the cyclic four-dimensional cyclic polytope with 7 vertices. And so we have found many stacked balls inside it as a subcomplexes. And there is a certain parameter which is called epsilon that I considered in here, and I wanted to minimize this epsilon parameter. And then I choose one of them, and after that I go through the same process over and over again. And surprisingly, when I arrived at the end, so the size equal to 21. I get K21, which satisfies the following property, that there is a facet G hat such that when I remove this facet, the transversal number has exactly 11. So this gives that actually this K21 should have the transversal ratio 11 over 21, right? Then how can we get the infinite construction? So actually, I had a very ugly infinite construction before, but when Michael saw that, so actually he suggested to find a much better construction. And after some discussions, we could find it. And actually, you can see so it looks like a train, right? And how we can find this kind of train-like look like a construction. We start from so actually this is again very misleading because this is two-dimensional picture, but this should be three-dimensional picture, okay? And this should be changed into the three-dimensional, the boundary of four-dimensional cross polytope. But after that, so except for that, everything should be similarly applied. And so by plugging in K21, by attaching K21 for each of the antipodal facets, as you can see, this facet is antipodal to this one, right? And after that, we attach another cross polytope where one of the pair of the antipodal facets have this one, and another antipodal facet go with this one, and we plug in the K21 in here, and so on and so on. So this is how the construction has been made. Is there any other question about this? Yes, in the next step, we constructed another cross polytope with one face in here and another antipodal facet in here. This should be triangle, and this should be this should be connected something like this. And we plug in the K21 to the antipodal facet of this big green face. Okay. And so on and so on. So this was the construction. Okay, and so since there are not many time, we need to go a little bit quickly. Okay, but actually piece one, the first piece is the biggest one. So actually, so I visited Technion in 2019, and as always, I presented this problem at there. And actually, so I could meet Joseph Briggs there, but he asked another. Yeah, he asked another problem that I never thought about it before. So he said to me the following. So you remember that there is a bound on the upper bound on the transversal number for the two-dimensional case. But he asked that, are you sure that this n over 2 bound is the tight bound? Do you have a lower bound construction for it? And then actually, so I just found that there are, so I did not really think about it before. Okay, so after that we have constructed this kind of ones. So this is almost the tight examples that we could have constructed before. But the problem is that to have an infinite construction, we need to have a kind of the inductive way of construction. But actually, we could not really find such a thing. But after Joseph saw this picture, he thinks that maybe this picture can be used somehow. Yeah. Yeah. So, but I doubt it because I failed before. But he said that I'm an optimistic person. And his optimism was correct. And the construction is something like this. Yes, so the result is the following. So this is only, this statement is for two-dimension case. And there are the result says that there are infinitely many two-dimensional spheres K with a transversal number K is exactly equal to n over 2. Okay, so how can we construct this? So the building block is, there are two building blocks. One is the tetrahedron. Always we are considering only boundary, but anyway, so we have a simplex, three-dimensional simplex and its boundary. Another one is important. So we have the octahedron in here. So I mean the three-dimensional cross polytope. But actually there is one thing, so one tetrahedron which is attached to the outer face of the octahedron. So this is the top face. So I mean the octahedron is somewhere in here, and the tetrahedron is attached in here. So and the red vertex should be the bottom vertex when they are attached to something like this. But if it is drawn, if it should be, it is drawn in the plane, then so this is the only possible way to describe this. But anyway, so this is a little bit more complicated structure and so on. And so anyway, so these are two building blocks, and this is the first step. I mean, you don't need to care about these two, but you only need to care about this subscript. Okay, so this is the first step, and the first step starts with the boundary of the three simplex. Okay, and after that we have the x22. So this is the second one, and how can we get it? So we get it by attaching this tetrahedron with one of the facet, one of the center facet, center face of the C2+. So actually you can see the outer face, right? Outer face of the octahedron, and this is the exactly antipodal facet of the outer face of the octahedron. And we attach that with this. And as you can see here, so I specify these red vertices in here, right? And these red vertices is a kind of what I call the base vertex. And the outer face should have always, so outer face should have the newly added, the most newly added red vertex like this. Okay, and this outer face will be attached again the antipodal face of the outer face of this octahedron, right? So as you can see, this is the outer. This was the outer face of the octahedron, and this is the antipodal face, and this is attached like this, and so on. So I don't have the time to give a proof, but I can give you the exercise because it is not very difficult. But anyway, this is the correct answer. This is turns out to be a correct answer. And actually, we could a little bit generalize this result to the arbitrary d, like this. So when you plug in d, d equals 2 in here, this becomes 2 over 4. Okay, so this was the second piece, and I'll just briefly introduce the third piece. And this is about the chromatic number. Actually, so the thing is that we could not really get a non-trivial upper bound on the transversal ratio of the tau, which is a tau k over n. So I got interested in just the chromatic number of it, and by this relation, if you get the upper bound on the chromatic number, you can get the upper bound on the transversal ratio and vice. And also you can, if you get the lower bound on the transversal ratio, you can get a lower bound on the chromatic number, and so on and so on. And actually, so the previous result was this. So actually this is a little bit general situation. And the previous there was a previous result by Heise, Panagiotou, Pikhurko, and Taraz, and which obtains the upper bound of this size for the so-called linearly de-embeddable classes of the simplicial complexes of the D plus and the D plus 1 uniform, satisfy the D plus 1 uniform condition. But we could improve that a little bit, slightly, a little bit in the exponent in here. So this was the result. And how we could get it? Actually, they have used the lowest local lemma in here to get it to the directly get it to the transversal number. Chromatic number. But actually, their result and our result is that they only need to consider the hypergraph itself. But actually, we also consider all the sub-hypergraphs which is contained in the hypergraph. That is a small, that is a little bit different. So we are using the more information. I think that is the reason why we get a little bit more improvement in here. So let us look at briefly. So actually, I just briefly introduced this class because what we only use, and actually this is what we really want to improve. Because I like to use the more specific and more concrete geometric conditions. But unfortunately, what we could only use is just using the upper bound on the number of hyperedges. And it is known that it is kind of another upper bound theorem is that whenever we have a geometric hypergraph which satisfies something like this, we have this bound on the number of hyperedges. There is another lemma which says that, so actually this is a very famous argument using alteration method. Bounding the independence number, and if we just modify a little bit, it just says like this. Then what we said is that whenever we have this one, and whenever we have this one, then maybe the number of the color classes should be n over something like this. Because this should be like something like the size of the independent set. So yeah, if we divide the n over the size of independent set, it should give the number of color classes. And actually, this intuition is correct, but it is a little bit involved. And so we three others discuss about this a lot, and we could get the following lemma, and we applied it. But I believe that this kind of construction and this kind of argument should be very famous, and I think there are many people who are familiar with this. So if you know, or if you have seen any kind of this kind of argument or result before, then I would be very happy to discuss about it. I like to see other examples which is very similar with this, but I could not find it yet. Okay, so this is outro, open questions. Okay, so yes, so actually I think I really admire Chris's comments and the intuition about this problem. Yeah, but still I think this problem is too big. So if you consider this question by Professor Holmsen again, this problem is very big. So, but I want to have some more improvements about this problem. And I'm not really sure about the answer, but I'm more on the side that the answer for this question is no at this point. Maybe I can change it. It can be changed. So if the answer is no, then we need to find the counterexamples, obviously. But how can you obtain the higher dimension, counterexamples for higher dimension, just for 1/2? Or what about the getting a counterexample for bigger alpha d, or the realized cases like a polytopes or something? So these are still out of my hand. I don't know how to do that. But if the answer is yes, then we need to start the investigation from the relatively small classes. But all the upper bound arguments that we have obtained before is just using the coloring bound. And we don't know anything more than that. And so I want to have another argument, getting the transversal number for simpler cases, including this one. So what about the stacked spheres? There is something called the stacked sphere, which is the boundary of the stacked d+1 ball. And the fact is that the transversal number is somewhere in between this number and this number. And question is, what is the exact maximum transversal number for stacked spheres? And I think this is the most simple case that I can think about. So maybe it is the first thing to just get through the stacked sphere first, then other cases. Okay, that's it. And thank you for your attention. Yes. Yeah. Yes. Are you asking that is that bound tight or not? I don't know. D equals 2. Let's see. So I don't think so. It should not because this is an infinite bound. But if D is equal to 2, this should be infinite bound. But we have the 4-color theorem and all the hypergraph. But this is the linearly 2 embeddable. This should. So this is still a planar graph. So yeah. So I think we should still have the chromatic number, which is a finite. So actually, it should be the number 2. Yeah, we should have the number 2, but it is an infinite bound. Yeah. So actually, 2-dimensional case is more or less done. But yeah. Yes. Oh, okay. So where is it? Yeah. Oh. I mean, even the coefficient? Yeah, yes. I think that is upper bound theorem. Yeah. But actually, there is one comment that I want to make. Yeah, so there is one comment that... Huh? Oh, yes, that is what I wanted to say. So, yeah, because if we change this linear into topologically embeddable or something, this is not known. This is not known. Yeah. So I think so yeah. So actually I hope so. Yes. So what I understand is that there is a fine extension, and so there is a map. Yeah.